Hello everyone, I'm Matthew and my friend Michael will talk about deep learning for image segmentation. So, yeah, okay, better. Okay, so here is our agenda and what we are going to talk about. So, firstly, we shortly introduce the segmentation task in computer vision. Later we move on to deep learning methods for image segmentation, and we will present case study on clothing parsing, so in fashion industry. Okay, so segmentation in computer vision, and maybe starting from general task which we can distinguish in computer vision. So basically we can distinguish three different kind of tasks in computer vision. The first one is classification, when we would like to just predict the annotation that something is on the image, that something is present on the image, or image has some feature. So for instance, on the image on the left, we would like to predict that there is a dress, or heels, or bag, or glasses. The other task we could define in computer vision is object detection. And sometimes we could distinguish object detection and object localization as different tasks. But object localization is actually it's just object detection, but it's for one kind of object. So object detection is a little bit more difficult task, as we need to predict usually tight bounding box around the object which is present on the image. Sometimes it could be ellipse or some different shape, especially in case of face detection. And the last task the task we are going to talk mostly tonight is segmentation. In segmentation, we would like to assign a label to each pixel on an image to completely understand the scene which is present on the image. And as you can figure out, it's the most difficult task that you have in computer vision, because you need a lot of information about each pixel, and you need to predict actually the correct value for each pixel. So let's move on to segmentation. So in case of segmentation, we can distinguish two kinds of segmentation: semantic segmentation. In semantic segmentation, as in every kind of segmentation, we annotate each pixel, but we don't differentiate objects. So basically, in the image on the left, we segment the image, and we know that there is a grass and a cow, but we don't know how many cows are on the image. And sometimes it's very important. For instance, let's take a case from fashion. So when we do the human segmentation in an image and the people are overlapping, then we have a problem to assign a clothing item to the correct person. And especially if there are different genders, this could be the problem for image retrieval, to search in correct shop, in correct products from correct gender. So there is more specific task in case of segmentation called instance-aware segmentation, where we try to detect instances, segment these instances. And it's sometimes called simultaneous detection and segmentation. It was recently introduced in ImageNet Challenge, MS Coco, in 2015. It's more interesting task, but also more challenging. But it's very tempting to resolve this task for many applications like image retrieval or some recommendations, content-based, and something else. Okay, so how we can resolve the segmentation problem? So back to 2012, we used some traditional methods. So on this slide, there is presented a horrendously complicated pipeline from paper doll parsing publication. So the aim of this paper was to segment the image and annotate different clothing items on an image. So it had several steps like tag prediction and some style retrieval, iterative smoothing, and everything was based on computer vision features like histograms of oriented gradients or maximal filter responses. So this pipeline has a couple of drawbacks. The first one, it has several steps, so basically it can fail, the training can fail at each step, so it's not easy to train. Usually we aim for end-to-end training because it's much easier to train and much easier to develop, maintain. The other problem here is we use those handcrafted features which are very low level and not very good for semantics in high level, like detecting a hat or a skirt or a dress. And that was the way people were trying to do the segmentation a couple years ago, but now we have deep learning. So deep learning is actually it's the renaissance of artificial neural networks, which are with us for quite some time. So deep learning renaissance started in 2006 in Toronto and New York and Montreal by Jeff LeCun, by Jeff Hinton, Jan LeCun, and Yoshua Bengio. And everything started with deep belief networks. So deep belief networks were generative models which were used for pre-training very deep architectures. And when they figure out good algorithm for pre-training deep architectures, it was probably one of the first times when actually the training of deep architecture started working, except of the time when Jan LeCun did this for convolutional neural nets in 1991, but it worked only for French people. But in computer vision, the main building block in deep learning is convolutional neural net. And everything started in 2012 with AlexNet, which is presented here on the photo. And AlexNet was quite a deep net at the time. It had 7 layers, and it has beaten all the other models in ImageNet classification challenge by a large margin. And since then, convolutional neural nets are winning each year the object detection task, the segmentation task, the classification task in ImageNet, and they actually are used by many companies in production. So moving on to deep learning methods for segmentation, we need to start with convolutional neural net, as it's somehow it's a black box and basic building block for all of the methods. And one important thing here, which will be helpful later, so in AlexNet at the end we have fully connected layers, and those fully connected layers can be treated as convolutional layers with 1-by-1 filters, and it's very important for basic methods for segmentation. So how we can tackle in the most simple way the segmentation problem with CNNs? So one may extract the patch from an image and try to predict what is the label for a center of this patch. And this way we could predict all the labels for all the pixels in the image. And actually for training it's okay because we can undersample these patches from an image. But the problems are in the test time, as predicting a label for each pixel it's very time consuming, so it's not feasible in production. And actually I did it once, and it takes for image 224 by 224 around 6 minutes on very good GPU, so it's totally infeasible. So how we can speed it up in the test time? So as I said before, the fully connected layers can be treated as a convolutional layer with a filter 1-by-1. So instead of feeding CNN with many patches, we can just feed with whole image and get the smaller mask in an output, but add once the mask for all pixels. But this method has many disadvantages, especially when we train on the patches. We have just local context and we lack of information of whole image. So there is no much improvement from the traditional methods. So the next thing which was introduced was fully convolutional neural nets. So the idea was, let's take a convolutional neural net and then learn how we can upsample. So we can get the initial size of an image and we can learn how to upsample this small output from the convolutional neural net to the big original output. And the basic operation for this, the main operation for this is deconvolution, and we'll talk about this in a minute. But here we can look at some examples from this publication. So basically we have the ground truth on the bottom image on the right, and we have some results. So when we have a convolutional neural net, this most semantic related to labels is in the last layers. When we're going area and area, we are more about features like textures or shapes or edges. And in terms of segmentation, to get quite good edges and quite good shape of actual object on an image, we would like to use that information. So you can see that when we just do the upsampling with deconvolution from the last layer of convolutional neural net, which is on the left image in the bottom image, we catch correct objects, but not correct shapes. And on the next image, we use 2 last layers, and on the next 3 last layers, so we can see the results are better and better. So that's the good idea, and actually there is a trend in computer vision for tasks like texture retrieval or some similarity learning to use the early layers of convolutional neural nets to capture the local patterns very good. Okay, so deconvolution. So deconvolution is the operation how we can, with which we can learn how to upsample to get the really good mask for a scene, for an image. So let's start with convolution. So the typical convolution, they are usually 3x3 currently, but it could be completely different size. So typically we use 3x3 convolution with stride 1 and pad 1. So for example, we have input 4x4, and as a result we get output 4x4. And how does it work? So the stride 1 means that we are going with a step 1 with a sliding window, and the pad 1 means that we are increasing the original input by a padding of size 1 around the input. So we are going with this sliding window, and we are multiplicating the filters. So the red square represents our filters, and the values of pixels are in the white box with many squares. So we multiplicating the filters with the values in the white box square. So it's image, just doing a dot product, and then we put the sum, so the result of that product into the output. And as you can see, we are going with a stride 1, so we just move by 1 cell with the blue square. So of course we can change the stride and we can change the path. So for instance, with stride 2, we get the output 2x2 smaller than before, like this, and still we're doing dot product, and that's everything. So during the training, we learned the filters, which here are represented by the red square or the blue square. So deconvolution is, so the first thing, in signal theory we have something called deconvolution, and it's a completely different thing than here, because deconvolution in signal theory is inverse of convolution. Deconvolution is actually the backward pass of convolution in the backpropagation algorithm. So it's very good for us because backpropagation is implemented everywhere, so we don't need special functions for deconvolution. And deconvolution is just multiplicating an input, a filters by an input, so it's like matrix by scalar, and putting all the values in the output matrix. And if they're overlapping, we just sum up. So here we have just one deconvolution, and there was this paper some time ago. Do we really need deep nets? And yeah, we do. So do we really need many deconvolutions, one may ask? And yes, we do. And it works much better when we have many deconvolutions. And it's very easy to set up because it's actually just upside down the original neural net with the operations we are performing in backpropagation instead of operations we are performing in the forward pass. So in the same year, there was this publication about deconvolutional neural net, and it worked much, maybe not much, but quite better than just one deconvolution layer. Yeah, so here we need one more operation to perform deconvolution and to reverse this VGG net. So in convolutional neural nets, we have two main operations, convolutions and pooling. So we know already how we can reverse convolution with deconvolution, but we need something for unpooling. So we can do unpooling this way. So in pooling, we are just taking some usually squares, and we are taking the maximum from square and putting in the pooled map with some strides. So let's say it's stride 2, so we have twice smaller output. And for unpooling, we need to remember from which place there was the max value. So we have something called switch variables. So now we can remember from where it was the max value, and with max pooling, we can put the value from pooled map into the correct place. In the other places, we have just zeros, so we lose information. But at least we put this value from pooled map into the correct spot. So, what's the how deconvnet compares with fully convolutional neural net? So, the two first rows are examples when deconvnet is better or even much better than fully convolutional neural net, but it also happens, like in the bottom row, that it's actually worse. So from the left, we have input image, ground truth, the result from fully convolutional neural net, then result from deconvolutional neural net, and this is that one with VGG upside down. eDeconvnet is ensemble, so it's a couple of deconvolutional neural nets, and we are averaging predictions from there. So ensembles usually works better, and ensembles are winning all the challenges, but usually it's not feasible to use ensemble in production time, in real case. And the last example adds conditional random field for sharpening the results, and we'll talk more about conditional random fields because actually they are very important for segmentation, but for now it's just a black box. It's some yeah. Let's leave it like that, and we talk soon about convolutional random fields. Okay. So Michael will talk about DeepLab, which was state of the art a couple months ago, but everything changes very quickly, so it's already not.
Hello everyone, I hope you hear me well. Okay, so let's talk something about the next model. As Matthew told, the DeepLab. DeepLab is basically a deep CNN with two nice additional features. But before diving into these features, let's see how this model works. So at first, we pass the input to the network, which is resized to some predefined resolution, and we do the feed forward over the network, and as the output get the so-called score map, which at each position contains the probability that the category is present for each category present on this position, and this output map is diminished by the factor of 8 in relation to the input. But later, next we take this score map, upsample it to the original resolution by using, for instance, bilinear interpolation, and later apply as a post-processing step conditional random field processing, and after it we have the segmentation mask. Okay, so it may worth to mention what's the architecture of the deep CNN. So in the paper, it's either slightly modified VGG16 architecture or much deeper ResNet architecture. ResNet actually performs a little bit better. But the modification consists of reducing the number of max pooling layers. In the original VGG16, we have 5 pooling layers. It downsamples the image by the factor of 2, so if we have 5 such operations, the output map would be decreased by the factor of 32. But because in segmentation we don't like to reduce our feature maps, our input too much, because we need to assign a label into every pixel, so there are only 3 such pooling operations. So later, the score map is upsampled by the factor of 8. Okay, so I mentioned about the conditional random field as the post-processing. Okay, then the first important thing is some slightly modified operation of convolution called convolution with holes. Okay, so let's talk something about conditional random field. It's quite a complex subject, so there's no time to talk about it, but briefly. It's a probabilistic graphical model, undirected model, which models conditional probability of one set of variables given the other set of variables. So in case of segmentation, we model the probability of label variables of our given the image pixels. And when we think about what we would like to have as the output of segmentation, it's exactly the probability which the CRF models. So, or to be more specific, we would like to find the most probable assignment of x's given our image. And because it's undirected probabilistic models, some of you may know that there are intractabilities here, even in computing the density function because of so-called partition function, which occurs in denominator here. So in order to find the most probable assignment of x, we need to rely on some approximation algorithms. And in 2011, researchers from Germany published a very nice paper based on variational inference, which solves the problem of finding this most probable assignment of x's. Okay, and the question is how the CRF interacts with a deep convolutional neural net. In this probability density function modeled by CRF, we have two kind of factors. The first one is so-called unary potential involved with every x, and pair potentials, which takes a pair of x's. So the deep CNN gives us the unary potential. Okay, and that would be everything about CRF, and later this convolution with holes. The other name is Atrowitz convolution. Okay, so in the traditional convolution, when we move with the sliding window over the input, we take the input continuously. So we take some part of the input, convolve it with filter, that is compute the dot product between the filter and the input, and store the output value in the proper position. But in convolution with holes, we skip some input variables, taking every second or every third value depending on the parameter rate. So why is it useful? We can perform the convolution with a larger receptive field because we are skipping some parts of the input without sacrificing the performance too much. So, for instance, we can take a larger context when performing the convolution. Okay, and the benefits of it are nicely illustrated in the paper published by DeepLab. So in the top row, at first we downsample the input by 2, and later perform some convolution with some given kernel. We have the output, and later we'd like to upsample the result of the convolution in the original size. But because in order to do the convolution we decrease the size of the input, we need to rely on some interpolation. So after the convolution we lost some information. Later we need to rely on some upsampling. But if we perform the convolution with holes, where we have a larger receptive field without sacrificing the performance, we can do this on the original input, and later have the output map, which is identical to the input resolution, without any upsampling. So it preserves the information. Okay, that would be enough about the deep learning models for segmentation. Now we'd like to present some case study. Okay, so segmentation has application in many fields, for instance in fashion. So we would like to parse the image, so we'd like to detect the segmentation mask for some clothing categories like bags, trousers, shoes. And why such a mask may be useful. So for instance, for computing the dominant color of the clothing category of the clothing. And because the segmentation problem is tackled in a supervised way, we need to have next to the images we also need to have labels for it. But the label here is just that for every pixel we assign a category to this pixel, whether it's a background, whether it's a skirt, and so on. And it's not hard to imagine that collecting such data set is very expensive, because it's unlikely to contrary to the classification task where we just put whether the category exists on the image. Here we need to do a lot of work to precisely annotate the image. And because of that, the biggest publicly available data set, to our knowledge, in fashion contains slightly under 8,000 images. And now a few words about this data set. This data set is called ATR data set, and there are 18, the categories set which is present there consists of 18 categories. So all of them you have listed in the right. It's publicly available. You can download it from GitHub. And here is the visualization of ground truth labels for each image. So for each image we have such an annotation. So for each pixel we have given to which category it belongs. So our goal here was to take this data set, divide it into the train and test with regard to some ratio, and check how our model performs on the test set and measure some numbers. So we aim to solve this problem in two ways. The first one is just to train a general segmentation model. We chose the DeepLab model based on the VGG16 architecture. We tried both variants with and without CRF post-processing steps. And when it comes to training details, we fine-tuned the original VGG16 trained on ImageNet. And we set some batch size, some number of iterations, and the train test split is 0.9. Okay, and here you have, so at first the visualization, how it performs on the test set. So you have the input on the left, and on the top right you have the ground truth mask, and below there are the predictions of the models, of the DeepLab model, with and without CRF. On this example, you can see it works quite well. In CRF, as you can see, the mask is more sharp, and what's more, this mask is rather more consistent. We'll see later in how they perform in numbers, but this is the second visualization. Again, it seems that the post-processing with CRF helps a little. Okay, and now numbers. Okay, maybe a few words how we measure the performance of the model. Because segmentation is basically a classification of every pixel, so we can measure the performance by using the metrics like accuracy, precision, recall, this stuff which comes from the classification domain. But in segmentation, the better metric is so-called intersection over union. So it measures how well our prediction intersects with the ground truth mask. Let's take two categories, that is bags and dresses. And as you can see, we have the DeepLab without CRF post-processing and DeepLab with CRF. So in terms of intersection over union, you can see that the post-processing steps helps a little, gives us additional 3% of the IOU, and the same applies to dresses. The gain is even bigger here. Okay, and I mentioned that we tried two approaches. So this is one. The one is general segmentation, and the second one we tried to combine this segmentation with detection of the object at first. So when we want to segment the image for some category, at the beginning we use some detector which gives us the bounding box surrounding this clothing part. And we can use many models available, for instance RCNN, SSD, or YOLO, and others. So at the first we need the detector which detects the bounding box around the clothing, and later we perform the segmentation only inside this bounding box, but we perform it only with two classes, that is background and foreground. We need to decide inside this bounding box, which pixel belongs to this clothing or belongs to background. And why we decided to check this approach? At first, collecting the data for detectors is much easier and much cheaper than collecting the annotation for segmentation. And second thing is that segmentation inside the bounding box is probably much easier than just segmentation over all image with some bigger set of categories than 2. Okay, and we decided to use the SSD detector, which stands for a single shot detector. It's quite a complicated model in terms of both architectures and training, so I'm not gonna I'm not gonna describe it, but we should remember that it just outputs the bounding box for some categories coming from the predefined set. And it's worth to mention that SSD is really fast in test time. It's able to process about, as I remember, 30 images in second, or even more. So it's and also it's quite accurate. It's one of the top models on some data sets. Okay, and some details about the training of the SSD. So we trained it for bags and for dresses categories. The bags data set was about 4,500 of images, while the dresses data set was much bigger. But it appeared that the SSD on bags performs much better, which is reflected by the score. There is bags MAP, that is mean average precision, but while on the dresses its score is much lower. So it's an important thing to remember when okay. And let's see in numbers how this second approach compares to the first one, compares to the general segmentation with deep lab. So on bags category, this detection with segmentation has much higher intersection over union, and general on bags it worked much better than our first approach. But when it comes to dresses, the score of the second method is somewhere between the deep lab without and with CRF. And this is mainly, we suspect that it's because of much worse performance of the detector on dresses, and it's okay. And while on bags, the detection performance was nearly excellent. So on dresses it was quite average. So it probably caused the much lower score on dresses. Okay, and that would be everything. Okay, and some visualization of this detection and segmentation approach. So it's I think it's clear how it works. At first we detect, for instance, for back, we detect the bounding box, and later do the segmentation. Actually, we also use deep lab, but with two categories to differentiate the object from the background. Next example. Yeah. Okay, and some technical details briefly. So for experiments we used Caffe framework with Python. There's publicly available deep lab implementation in Caffe, so it's not difficult to use it. For SSD we also use the Caffe branch. SSD, and we've taken the deep lab architecture from a publicly available site where all of the models were attached by the authors of the paper. Okay, that would be everything. If you have any questions, feel free to ask.